last video, I talked about the different types of intermolecular forces, and I briefly touched on intramolecular forces. So I'm going to, in this video, take all of the different attractive forces that you will see, and I'm going to review them. So the first type of attractive force is an intramolecular force called ionic bonding. Now remember, in an ionic bond, you have metal and a nonmetal with a positive and a negative charge. And so here are some of the characteristics of ionic bonds. The first is that as solids, they do not conduct electricity, and that's key. When they're dissolved in water, however, they do conduct electricity, and that's because when they're dissolved in water, their ions are free to move about and to conduct electricity. They're not held tightly in a solid, and therefore the flow of electrons is much easier because the ions themselves are free from that rigid solid. The next characteristic is when they're solids, because there's a really strong attractive force, they have very, very high melting points. Metallic bonds exist when you have metals. So here you have gold, and the way that we describe metallic bonds is that we say it is an electron sea, meaning that you have a bunch of gold atoms, and instead of sharing or donating their electrons move freely through all of the different metals. And so it's a sea model. Now let's look at some of the characteristics of metallic bonds. The first is that they have a high melting point, not as high as ionic bonds, but still a high melting point. It takes a good amount of heat to melt a liquid. And they are great conductors of electricity when they're solids. And so that's how they're different from ionic bonds as well, because they're great at conducting electricity even when they are solids. Covalent bonds, there are going to be two different types that we look at. The first that we look at are just molecular solids. Molecular solids are discrete molecules like carbon dioxide or any of the other molecular compounds that we've looked at. And so when we're describing characteristics of molecular solids, what we use to describe them and to dictate what they're going to act like, we look at their intermolecular forces. So whether or not they're polar or nonpolar, and therefore if they're going to have London dispersion forces, hydrogen bonding, or dipole-dipole forces. Remember, hydrogen bonding would have the highest melting and boiling points, while London dispersion forces would have the lowest melting and boiling points, simply because London dispersion forces are the weakest type of intermolecular force. So those are molecular solids, which we've already looked at. The other characteristic of molecular solids is that they cannot conduct electricity, period. No matter, even if you try and dissolve them in water, which unless they are polar, you aren't able to, but they do not conduct electricity. The other type of covalent bond, the other form it can take, is in the form of covalent network solids. Now, covalent network solids might sound new and unusual, but you've actually had a lot of experience with them. They have an extremely high melting point, and they have an extremely high melting point because, as you can see, for example, for diamond, a covalent network solid consists of atoms that are all tied together by covalent bonds. It's not a molecular solid in which there are covalent bonds, but then they rely on intermolecular forces. All of the attractions in a covalent network solid are the intramolecular force of covalent bonding. And so as a result, they have a very, very, very high melting point. And two examples that you see on a daily basis are diamond and graphite. Now, really just as a quick aside, graphite it looks way different than diamond. It's an allotrope of diamond, meaning that the bonding is just slightly different. And the reason why is graphite, the covalent bonding exists in layers between those carbon atoms, but then there are actually gaps. And as a result, graphite forms sheets, as opposed to diamond, where all of the carbon atoms are attracted to one another. So that's why graphite's so easy to use to write, because those atoms will simply move past one another very easily, but still extremely high melting point. So if we're comparing melting points, covalent network solid has the highest, followed by ionic, followed by metallic, and then followed by covalent. As far as conducting electricity, metallic is the one that conducts electricity as a solid. Ionic will if it's dissolved, but the other two will not. The last concept I want to go over is boiling point and vapor pressure. Remember, if the attraction between molecules or within molecules is very, very weak, then it's easy for those molecules to either melt or vaporize. And so as a result, if you have very weak intermolecular forces and intramolecular forces, If you have very weak intermolecular forces, then the amount of that compound that is a gas is going to be very high, meaning it has a high vapor pressure, because that's a pressure resulting from the vapor. Now, a key concept for you to know is that in order for something to boil, the vapor pressure must be equal to the atmospheric pressure. So as a result, if you have a compound that has very weak intermolecular forces, it's going to boil at a much lower temperature. And that is because it's much easier for its molecules to go into the gaseous form, and therefore it's not going to take that much heat in order to get that compound to boil. So remember, the strength of these intermolecular and intramolecular forces is key, because the weaker that attraction, the lower the boiling point and the lower the melting point. The stronger that attraction, the higher the boiling point and the higher the melting point, meaning more heat and more temperature is required in order to break the attractions between those molecules or atoms.